Good evening. The class will begin in like 1 minute. Okay, so welcome to the week 3 of the Mechatronics. Welcome to the week 3 of the Mechatronics problem solving session. And we'll first, once again, begin with a small recap of everything we've done over the last 6 lectures. 5 lectures. Lecture 11 Lecture 11 talked about mechanical actuations, and we first defined a lot of concepts about mechanisms, links, and the like. We talked about degrees of freedom and then moved on to constraints. And one important part about mechanical actuation is the concept of kinematic chains. The one of Understanding the Grashov's criteria is also kind of important. Then we moved on to gears, and we talked about different types of gears, and the prof showed us several kinds of gears. One of my favorite kind of gear, which would be the planetary gear system, that was not shown, but that's fine. And finally we talked a little bit about bearings and motors. Is there any specific questions about the lecture 11's material? We will solve a couple of questions based on kinematic chains and kinematic chains. We'll talk about motors mainly in the electrical actuation section. If there are no specific questions about lecture 11, we'll continue to lecture 12. Lecture 12 talked about hydraulic and pneumatic actuation systems. The first solid 12 slides were based upon the differences between these two. I do not think I will have to repeat all the differences, but the main differences are in terms of the maximum pressure and the speed of the elements and the like. And then this lecture had the most number of new symbols and concepts. So we will solve a couple of questions based on these a little while later. The concept of the directional control valves is kind of new, and I think it'll be very nice if all of us solve a couple of questions based on these. And that kind of concludes lecture 12. Is there any specific questions about lecture 12? There is an entire section about cylinder sequencing and things like that, and I feel that's quite important. We will solve a question on that eventually. Then we have lectures 13 and 14, which talk about electrical actuation. Electrical actuation naturally is one of the most significant part about mechatronic systems, essentially because electrical systems are just so convenient to use. We began the lectures using the things we've learned in 12th and 11th about how electricity and magnetism is related to the force, and the entire concept of electromagnetic induction. Eventually we talked about electrical switches, which are also known as relays. And after that we've properly set up the equations for motors. There are several kinds of motors and different equations for each of the motors. The simplest motor okay, we cannot exactly say what the simplest modeler is. All of them are equally complicated and wonderful in their own rights. But the first one we studied was the brushed motor, or in the lectures it was given as permanent magnet DC motor. We looked at the equations, we looked at different types of permanent magnet DC motors, and also how to control each of them. Then we studied about the BLDC, that is the brushless DC motors. Then in lecture 14 we also talked about the single phase induction motors and the synchronous motors. After that we took a detour back to stepper, because stepper motor looks more similar to AC. The operation of stepper motor is closer to how it works for AC motors, but in the stepper motor is in the end still a DC motor. So hence how I've explained it here. And then sir gave us a lot of questions on how to select the ideal motor for an ideal application. That's the brief overlook of lectures 13 and 14. Lecture 15, which is the most theoretical and least problem solving of the lectures, involved data presentation systems. We first talked about how measuring the data itself can cause a change in the value of the measurements. The best example is measuring the voltage in an electrical circuit. Then we looked at different kinds of measuring data, different kinds of display units, like the oscilloscope, the visual display unit, printers, and so on. I do not are there any questions based on specific questions you have about lectures 13 and 14 and 15? Okay, if not, we'll first talk about a couple of last week's queries. Give me a second. Okay. In last week, one query was the difference between settling time and rise time. Give me a second. I'll just make sure I got the the difference between settling time and rise time. Yeah. Sorry. Response time and rise time was not clear. Rise time was defined in the lectures as unfortunately I've went through the book and other materials as well, and essentially the major difference is that the rise time depends on our depends on what the rise time depends on we have certain choices to make for the rise time, in the sense we decide what the specific percentage is. Meanwhile, for the response time, it is always considered to be of the 95% of the output. There was one more question about last week, but I think that was more about administrative stuff. So in case any of you have questions regarding the marking of the answers in the assignments, what I've been told is you're expected to ask the questions in the discussion forum, and other TAs who are involved with marking the questions and generating the questions will reply and give marks accordingly. I am not able. I can only refer you to them, and that's only via the discussion forum. So I'll write it down. Queries regarding answers should be asked in the discussion forum. Yeah, so that includes all the questions you've had about the difference between writing closed instead of close, and writing closed loop instead of close, and things like that. Even the question about the thermocouple, in which we have given both high temperature and low temperature, if you ask that in the discussion forum, I'm sure they'll give you marks. Now we'll go to one part which I like, and that is the kinematic chains. In the example, Sir had told us that the Grashoff's criteria is the one for which I guess it's better to show how the Grashoff's criteria works. So here I have a 4-bar linkage. The first bar will be the ground bar, which will connect. Wait, I'll just add that. Okay, I can't add it right now, but imagine there's a line which connects these two. So that will be the first link. The link lengths are as follows. I've right now just given random values, and I've calculated the max plus min. What Grashoff's criteria essentially says that if the value G1 I'm calculating here, if that is less than G2, then the smallest link is capable of pure rotation. Otherwise, if the Grashoff's criteria is not valid, then not every angle is possible. I mean, none of the we can show this easily in a while. So say I increase, if I do that, yeah. So in this case, the max plus min is greater than G2. The sum of the shortest plus longest link is greater than the other two links, and therefore for these range of angles, the small range of angles, it's not possible to have the other two links collide. So evidently, if you, not every pure rotation about this angle is not possible. Likewise, you'll see a pure rotation about the other angles are also not possible, and it's just a matter of writing the equations and seeing it. On the other hand, if this will be an interesting case, because right now G1 is equal to G2, and you will see that the thing will satisfy. And you can see how, given a specific rotation of this link is just rocking. So this is often called the crank rocker mechanism, because one of the angles is, if we are cranking one of the angles is going a pure 2 pi degree rotation, and the third one is, the last link is just rocking around. Like the part taken by the last link will be a arc of a circle. Does that make sense? We can also change this little more, and now we can change most angles. For very specific orientations of L1, L2 and L3 and L4, we'll get a double rocker mechanism. So I believe that will be making these two equal. 0.4, 0. Come on. And So I have in my animation I forgotten to include the equations for double rocker. As I've accidentally forced the top angle to always be will always pointing down, and therefore I can't have a double rocker. Otherwise, this would have been a double rocker. I'm sorry. So that is about the Grashoff's criteria. Is there any other questions about Grashoff criteria? Wait, am I audible? I am audible, right?
Yes.
Okay, thank goodness.
Yeah.
Okay, another thing we can see can be the a question. Yes.
Uh, Here that G2, why it is not fully not rotating?
I didn't get you.
That G2, the link second, almost the both are the same dimension. It was halfway. It was rotating 180-degree only rotating. It's not. There is no full circle.
Oh, so you're asking why this one is just going top and not going the other way around?
Yeah, yeah.
That's because in my in the equations I've written in the animation, it will.
Okay, okay.
Yeah, so I didn't include this. The special case of double. Like essentially, when I'm doing this, the I have constrained the top angle to be. I've always constrained this point to be above the x-axis. Otherwise, if you think about it, wait, give me a second. Like
Yeah.
both conditions are possible. Where did so in addition to this, it's also another way would be. Oh wait, no, just parallel to that. Like this sort of thing is also possible. Now, right now, this was pointing up. This one is going that direction. This one is also possible. The only reason it's not is because since we have constrained, we had the choice initially to constrain what direction the ranker moves. Sorry, the rocker moves. Like when I was writing the equations down for this, I was thinking of this will always be a crank rocker, and therefore I must specify which direction the rocker is facing. So wait, give me a second. L2 should be yeah. So here, this is definitely a rocker, right? So the different thing is there are always two orientations possible for a rocker. I can either have it on the top always, or I can have it on the bottom, and both of them will have slightly different equations. And I didn't want. I had forgotten to note down the other set of equations also. I can show this in the next class if you want, like how this can have another set of equations on one on the bottom. Like unfortunately, the equations slightly painful, and therefore I don't want to waste time writing the equations here. It could take a lot more time than I expected. But you're right. If I had done the crank rocker properly, the thing would both of them will continue cranking. Sorry. I'll just try one more thing. Yeah, so ideally it would have always I should have done the crank rocker thing using both keys. Yeah. This was just a demonstration of the crank rocker and the how the Grashoff's criteria shows you that if some of these two is some of these if G1 is greater than G2, then will never be able to have a pure rotation above any angle. Anyways, after that, let's go to hydraulic and pneumatic, and we have a few questions we can solve about this. So consider this case. We are having a directional control valve, and let's consider, if say we are not pressing this button. I will take the questions from other place. Would you like to solve this? I'll give 3 minutes. It shouldn't be too difficult. Okay, so do we have any answers? Okay, so if the push button is not pressed, let's consider what happens. If the push button is not pressed, then this is the region you have to look after. Remember that this symbol represents the source, and this symbol represents the exhaust. I'll write this more neatly. So, if the push button is not pressed, the pressure is applied to port 4, which makes sense because we have the source here, and it's uh, providing pressure to the port 4, and port 2 is connected to port 3, which is the exhaust. That means for this, the answer will be true and true. Say if you are pushing the if you are pushing the can you solve this now? As in, what happens when the push button is pressed?
I
Okay.
think both are FF. D.
Okay, let's see about that. Give me a second. So, if the push button is pressed, the source, which is in port 1, will give pressure to port 2. Therefore, 1 is false. We can strike these off. Port 2, we just agree that port 1 is connected to port 2, and that means port 4 will be connected to port 3. Therefore, port 2 is not vented. So both of these are false. That means yes, you are right. I will just mark this slightly better so when other people look at this, they'll understand. So that's wonderful. Then we have another question kind of like this. Give me a second. Like earlier, I decided to read out the question, and I thought I wouldn't have to put the questions in the paper, but I guess it's better this way. So here we have a cylinder connected to two valves, and the first question is, I hope the question is clear. So question is, once again, check if the first one is true or false, or check the validity of both statements. Just once again, this is the source and this is the exhaust.
It may be true and false.
That's correct. We'll go through the answer again. So when the push button is pressed, that means we have the port being connected to the I'll just number this. We'll have the port being connected to 2. That means that that pushes the load up. Therefore, it makes sense. If when the push button is pressed, the load is lifted. When the push button A is released, the load descends. That is not true. The load will only descend if the exhaust is turned on. So we have true and false. True for the first one and false for the second one. That and yeah, that means this is the answer. The next question would be, I had accidentally skipped a question in the previous one. We'll just do that. Yeah. So for this old question again, say we now we have released the push button. Is this true, or can we check the validity of these statements? Yes? Oh, someone wants to enter. So if the push button is released, that's essentially the same thing as the original case. And we already studied that in the original case, the pressure was applied to port 4. So this is definitely false. And likewise, the earlier we had said the port 2 was vented. So this is also false. So this will also be a D, false comma false. I hope that made sense. The important thing here is we are releasing the push button, and therefore it goes back to the original case. This is essentially mainly because there's a spring here to bring us back to the original state. I hope that made sense. Okay. So we'll solve another question based on this. So the question is again same as before. Can we check the validity of these two statements?
The question that it's a little bit enlarged occurred because
Okay, I can do that. I was pretty sure I could do that. Okay, that's another way to do it.
yeah, it's
Yeah,
clear
yeah.
now.
Oh, you might want to see this also.
Yes,
Yeah, yeah.
yes. Okay, now I got it. Please. And it should be, it may be option C.
Yes,
Yes.
it is option C.
Yes, that's correct. So we'll go through this slowly again. So when the push button B is pressed, they are saying the load is lifted. Let's see what happens when the push button is pressed. When this is being pressed, that means the exhaust is switched on. If the exhaust is switched on, that means the load will descend. Therefore, the load is not lifted. This is wrong. So we can cross out these two. When the push button B is released, that means the load is either lifted or descended. So if the push button B is released, that means it will be in normal configuration where the exhaust is not linked to the port. If the exhaust is not linked to the port, that means the pressure inside the cylinder cannot be released, and therefore the load will remain where it is. Therefore, C is this is correct, and therefore the answer is C. Nice going. Give me a second. Let me check if there's one more question. Okay, so I hope that this part of the things made sense. The next question, I'm giving a small warning. It's slightly bigger. So the question here is, what's going to happen after you press start? As in, there is this. I mean, essentially, after you press this push button, essentially after you press this, then maybe cylinder A will extend, or maybe cylinder B will extend, and after that maybe cylinder B will descend first, and then A will descend. Who knows? So that's the question. What's going to happen? I can give options if you want, but essentially the question is, what is going to happen to the cylinders after you have pressed this start button? In case you want options, I will write it here. I hope the diagram is visible and I don't have to L nudge.
Yeah, it's
Okay,
visible.
okay, fine, fine.
No, can you repeat that question?
Okay, so question is essentially, when you press the start button, when you press the start push button, then naturally because of these joints and because of these sensors and stuff, the cylinders will be pushed or pulled. There are two cylinders here, right? Depending on how these ports are arranged to each other, they will be pushed or pulled. The question is essentially, which what is the order it's going to be pushed and pulled. Like this means that first the cylinder A is pushed, and then cylinder B is pushed, and then cylinder B retracts, and then cylinder A retracts. But this is just an option, it might not be right. The other option. I'll give some more time for this question because it is slightly more involved. So should I start, or do you want some more time? Okay, so when the push button is pressed, the first thing that happens is the source will connect. I'll okay. The first thing that happens is that the source will connect to port 2. naturally, because that's what the push button does. This section of the button will move to the proper place, and therefore the source will connect to port 2. Now as the source connects to port 2, what happens is, in this valve, there is pressure at port 1 now, and that will move on to port 2. And this source in this pressure in port 2 will push this this valve to the to this region. So since this region is activated now, we'll just draw these here again. We have we have the important thing to see is always where the source is. The source is here, and now the source is in the middle part, and it goes to the top left. When it goes to the top left, that means the cylinder is activated, and therefore the thing goes from A minus to A plus. That is, the cylinder A is extended. So we can just so the cylinder A is extended. The moment cylinder A is extended, a couple of things happen. The first thing that happens is, this is activated now. Because this is activated, note that since we are only pressing this push button for a short time, so we can assume that immediately after this has been extended, we are letting go of this. So now, instead of this being activated, we have this activation, and that means the cylinder A gets retracted now. I should explain this again. So note that right now cylinder A has been activated, and it's right now here. I'll use a different color. Because the cylinder is right now here, this this directional control valve will activate, and because this directional control valve activates, the source will give a pressure at this port. The source will give a pressure at this port, and therefore this region of the valve is activated. Now, since this region of the valve is activated, we have because the source here will push back the cylinder, we get that the cylinder A will retract. So now the cylinder A retracts. Because the cylinder A has retracted, because cylinder A has retracted, so frankly, we can guess the answer directly from this already. We found that the cylinder A retracts, and therefore it's not the options A or the option C. And clearly option 4 is ridiculous, because we cannot have the cylinder B retract before it is extended. So clearly the answer is definitely option B. But we'll see what happens to cylinder B now. Since the cylinder A has retracted, it's now at A minus, and therefore this directional control valve has been this region of directional control valve has been activated. That means it's this. That means, once again, since the source is here, the source will move to the source will activate the port, and therefore we will get this region of the directional control valve activated. And because this region of the valve is activated, we'll see that the source pressure activates the back of the cylinder, and therefore the cylinder B extends. Because cylinder B extended, the I'm out of colors. Because cylinder B extends, this directional control valve is activated, and therefore it's very trivial to see eventually that cylinder B will also retract at the end of this. So therefore the correct answer is this. I hope that made sense. I do not mind if explaining this again. It's a fun topic. A lot of this is essentially following each of the ports and how the which ports are activated because of the sources and so on. So does anyone want me to explain this again? Okay. So after this I have a couple of questions. We have essentially just reached the finished until hydraulic and pneumatic things. I think I've covered the essence of both of these so far. Now we'll look into some electrical actuation systems. One kind of simple questions will be like, consider you have a stepper motor whose a stepper motor with a 6 degrees 6 degrees per pulse. Say you have a stepper motor that moves 6 degrees per pulse. If so naturally this means that if you give a single pulse, the stepper motor will rotate by a measly 6 degrees. Say you have a microcontroller which and is providing 300 pulses per second. If it's giving 300 pulses per second, that naturally means it's traveling 300 multiplied by 6 degrees every second, and that will equate to degrees, which is 5 multiplied by 360. This means that if you're giving 300 pulses per someone is entering. So this means that if you're giving 300 pulses per second, that means the stepper motor rotates at 5 revolutions per second. That's essentially one of the small concepts about stepper motor. Other kinds of questions that you can see are involving the torque measurements of motors. I haven't. Okay, so this question is so boring. Okay. I am going to follow a question given which is there in Bolton, because essentially this question is just a lot of application of formulae, so it makes more sense to, and once you're familiar with the formulae, it's not too painful. So the question goes as follows. So say you have a motor and it's connected to a gear shaft, and this gear shaft is connected to a drum. Around the drum you have we have a pulley system around the drum, and it's carrying a load. The diameter of this drum is 0.5 meters, and the load is say 1,000 kilograms. That because the load is 1,000 kilograms, we know that the tension in this pulley will be T is equal to mg, which is equal to 910 Newton. So that means the drum requires a torque, since the drum has a diameter of 0.5 meters. That means we know that torque is equal to force multiplied by radius or distance. So in this case it will become 9180 multiplied by 0.25. If you plug in the numbers, you will get approximately tell you what, for simplicity, let's say G is equal to 10. So this is just 10,000 Newton. So this will become 2.5 kilo Newton meter. I hope these steps make sense. Now if you're say you're pulling this up at a speed of v is equal to 0.5 meters per second, that means the angular velocity of the drum is 0.5 divided by 0.25, which is 2 radians per second. I'll write. The question straight up says that, say the motor spins at 25 rpm. The motor spins at 25 rpm. But if the motor is spinning at 25 rpm and this is moving up at 2 radians per second, we must first convert this to proper radians per second, and that proper revolutions per second. Oh wait, it's easier to do this way. So 25 rpm is 25 multiplied by 2 pi rad per minute, which is 25 into 2 pi divided by 60 radians per second. If you simplify this, it's approximately 5 pi by 6 radians per second. So if you check the gear ratio, that will be the output by the input, and that give me a second. I'm sorry. So in the question it had said 1500 rpm, which translates to 25 revolutions per second. I read the question wrong, I'm sorry. 25 revolutions per second, and this translates to 50 pi rad per second. 50 pi rad per second is approximately 152 point something rad per second. When you divide, so that means the gear ratio gear ratio is like 152 point something something divided by 2, which is actually 75, but the textbook decided that it's fine to round up, and we get a gear shift of 1:80. Now, since the gear shift is 1:80, and we know the input torque is 2.5 kilonewton meter, that means the torque required by the motor is 2.5 kilonewton meter divided by 80, because that's what happens because of a gear. The gear can increase the speed while reducing torque, or increase torque while reducing speed. So when you simplify this, we'll get that the motor we are selecting should have a torque requirement of 35 newton meters. Yeah, 2500 divided by 80 is approximately 35 newton meter. So that is one kind of question you'll solve on this. As I said before, all this question is essentially just taking all the various formulae you have learned throughout and then just substituting them in. Another important formula is the one in which, say this load was actually accelerating instead. If this load was accelerating, then you would get that. Then you have to include the moment of inertia of the drum and the moment of inertia of the thing, and that means that you have to use this formula, that the effective moment of inertia is n square into I. And this was derived in the earlier classes. This is derived in the first class, if I remember correctly. The derivation of this goes by understanding the principles of how a gear shift works. If you have a gear shift, then the power is the one thing which is conserved. I mean, we have conservation of energy, and if energy is conserved, that naturally means power is conserved. We know power is torque multiplied by angular velocity. There are two sources of in the case of a gear shift, there are two torques essentially. There's one, okay, not two torques, there are two moment of inertia essentially. The moment of inertia of the load and the moment of inertia of the load and moment of inertia of the motor itself. So we'll call this IM and this IL. Likewise, the angular velocity of the motor is omega m, and the angular acceleration of the motor is alpha m. The angular velocity of the load is omega L, and the angular acceleration is omega alpha L. We know that torque is I multiplied by alpha. So power is essentially I into alpha into omega. Since we have to add the contributions from both the things, we'll get I m omega m alpha m plus I L omega L alpha L. But we know that these are related. We know they are related by a factor of n. That means IM plus IL, omega L is n into omega m, alpha L is n into alpha L, alpha m, and that gives us IM plus n square. Say they're related by, how did I make a mistake here? Give me a second. Oh no. I'm sorry, I wrote the equation here wrong. That's yeah. So we get, and I mean, so this doesn't matter. Like essentially, if you know how to derive it, sometimes you just don't need to remember the equations as it is. So we get IL into alpha m omega m, and we know power is usually from the point of view of the motor. So this means that the effect, this power is the power required at the motor, and the motor is right now going at omega m. That means the effective torque requirement will be this divided by the rotational velocity of the motor itself. So so we'll get the torque as Im plus n square IL into alpha m. That is how, in fact, the next question given in the Bolton book is literally application of this, just like that, without requiring any more thought. I have in addition to that, I do not think there are any questions in the first part, in the last part, in the data presentation part. I guess the most interesting part about this data representation part was the phase encoding and the frequency modulation. But I hope if there are no questions about that, I hope there are no questions about that. But there are not many questions I can generate from this. I searched for questions and I couldn't find many nice questions. There's also a little bit about ASCII, and I think yes.
Yeah, yeah. There is a Hall sensor. The If you refer the question at that,
This is a Hall
uh,
sensor.
Hall sensor. Yes.
Where's this question? Is this question in the
Yeah.
assignment?
Yes. That is Hall sensor generally used to sense of the speed motor. Uh, how to because it was not defined in that our classes, but answer is
All of the above.
uh, yeah,
The answer is all of the above, but you're
yes,
asking how the Hall sensor is used to sense the speed of the
sense
motor.
of the speed motor, because it was very clear in that last lesson that it's the sense the position of the rotor and sense the proximity also.
Yeah.
But since the speed of the motor, how where which lesson it was covered, I'm
So
not clear about that.
technically, it doesn't directly sense the speed of the motor, but given the fact that we know that if you know the exact position and we know how fast it's because we know the exact position, say it's say the we'll go to this, I guess. Yeah, wait, give me. So say we are getting the output from the Hall effect sensor time, and we get this output from the Hall effect sensor. That means we know we are getting like 4 pulses, and okay, we'll be okay. So let's make this like 10 seconds, 0 to 10, and I can't draw this. Okay, we'll just have a very simple setup with a 3 with like the 3 set of magnets. So if the Hall effect sensor is here, this will give an output whenever the the magnetic region of the thing comes close. So the first time it will come close is when this one reaches. Then later when this reaches, when this reaches, and when this reaches again. So that means in 10 seconds, this has rotated 4 by 3 times. That means, given the fact that you know how the pulses occur, and we know the time at we also know the time, then we can calculate the velocity. I must confess that you don't get the specific position. You won't get the velocity directly from the Hall effect sensor. You have to do a little bit of calculation to get it.
That question is my question is, when we calculate the speed of the motor,
Yeah.
There may be a counter should be there. So the position 1 and position 2 and position 3, it was counted with the period of the time. So where the counter will be recorded, like
I'm not getting you. So
yeah,
I'm saying that no, we don't even need to count. Essentially, if you know the time elapsed, if you just know this time, so in this case it will be 10 by 4, then you can figure out what the speed of the speed of the servo motor is, right? Because you know that in this amount of time it has rotated 1/3 of the it has completed 1/3 revolution. That I guess that didn't make so can I search Hall? So yeah, the slides don't tell you that the Hall effect sensor can I mean,
yeah, that's a question. It was not covered in the lecture. I was a little bit confused about that. That other sensor like counter, it was covered the angular velocity, or that is was very clear. Here, the Hall sensor, how it was like you explained, it's a number of position with the time period. We can count the velocity. So that number of time RPM, like speed is here, like RPM means. So this counter, how many time we need to count it?
give me a second. Like, Hall effect sensors are specifically used to get positions. So we have to do further data processing to get the velocity from it. So if your point is valid in the sense that we cannot directly get speed of the motor from the Hall effect sensor. That's true. We can calculate it later, but yeah, I would recommend that you add this to the discussion forum. Add this to the discussion forum. You might be able to get marks for this. Yeah. Like in the end, I'm not the TA who's giving marks for.
It's not about that asking that mark like that. We how to we can use that Hall sensor like 1 3 1
No,
like
no, you're right. You're right. With just the Hall effect sensor, you cannot get the speed of the motor. You need to have some data processing after that.
after that, like angular velocity, we need to count that one full revolution and get that again that same position. And suppose if start at A position, that again it was a position, and it may be the like if any motor count that, if maybe stepper motor or DC motor, the starting related to that some response time it was required, then only we can calculate that minimum time to the
Yeah.
count of
Yeah.
speed of the.
Yeah. Essentially, we need not just a Hall effect sensor. We also need a, like, essentially a timer to measure the time and things like that. Like, it's not like a normal taco generator which directly gives you the angular velocity as an output. So you're right. Yeah.
Yeah.
I've unfortunately gone through all the things I wanted to cover already, and if necessary, we can go through the electromagnetic principles of induction and things like that. I expected the pneumatic and hydraulic stuff to take more time. Okay. Okay, we'll check out some electromagnetic principles. So some questions which are there in. So one question which is there in Bolton is, say a stepper motor has a step angle of 7.5 degrees. How many pulses do you have to give to have to generate a velocity of, how many pulses for a velocity of 10 revolutions per second? This is not a difficult question, but yeah. So the question is pretty straightforward. We know that one pulse will give you a 7.5 degree change. That means for 10 revolutions, that means 10 revolutions corresponds to 10 into 360 degrees, which is 3600 degrees. For 3600, you and per each you have 7.5, and that's approximately 480 pulses per second. That's one of the questions in Bolton. Like, many questions in Bolton are just theory questions, like explain the principles of brushless DC motors and things like that. I don't think I have to solve questions like that. Another question which is given is, if a DC motor is producing a torque of 2.6 Newton meter when the armature current is 2 amperes, what is the torque when the armature current is 0.5 amperes? For this, we know that torque is equal to kT into I. So with this equation you can solve for kT, and once you get kT you can multiply here and get the answer. So most of these questions are just direct application of formulae. Another question. I think this question is slightly more challenging. Say you have a permanent magnet DC motor with an armature resistance of 0.5. armature resistance of 0.5 ohm, 120 volt is applied, and we are reaching a steady state velocity speed of 20 revolutions per second, and we are drawing 40 amperes. So the first question is, what's the power input to the motor? Second question is, what's the power loss in armature? And third question is, what's the torque? I'll leave you some time to solve this. I'll write it down. We don't have the data to get the torque. The first two parts of the question are pretty easy. The power loss in the armature, we are told that there's 40 amperes of current into the circuit, and we have 0.5 ohms of resistance here. That means that we know the formula P is equal to I square R, where that is the power loss inside a resistor is equal to I square R. That the power, so that means the power loss will be 16. Huh? didn't. Give me a second. So that means that the power input to the motor is clearly we have 120 volt of input and it's drawing 40 amperes. That is, so that when we know power is equal to voltage times current, so that means the power input to the motor is 4800 watt or 4.8 kilowatt. The power loss in the armature is P is equal to I square R, which in this case will be 40 squared into 0.5, which is 800, 400. Yeah. That means the net power we have. Okay, yeah, I'm so sorry. The torque is pretty obvious. Yeah, the net power we have is 800. The net power loss is 800. Now, for the torque, we know that torque multiplied by steady torque multiplied by angular velocity gives you power. Now, since the torque input is 4.8 kilowatt and the power loss is 800 watt, the power given to the entire motor itself will be 4000 watt. And since we know it's moving at 20 revolutions per second, we must convert that to T is equal. We must first convert that to radians per second. So that is 20 into 2 pi rad per second is equal to 4000 watt. That means torque is equal to this ugly number, 100 by pi Newton meter. So that's the kind of questions you get in this lesson. We went a lot faster than I expected. Okay, I guess we'll just quickly go through everything again. The first question first things I had shown. Okay, we'll first talk about the last quiz queries. The main difference in response time and rise time had been that the response time specifically. Give me a second, I need to look at it again. Yeah, if I remember correctly, the response time was between a very specific percentage. Response time has to be between 0 to 95%, while rise time is denoted by us, and it requires, what's that thing called? Like, we might sometimes say that it's from 10% to 95% and so on. And this is more up to what it depends on the manufacturer of the sensor and things of that form. So if you have any questions regarding any of the answers in the assignments, please do ask in the discussion forum, because I'm not the TA in charge of giving marks, and the actual TAs in charge of giving marks will read those questions and give marks accordingly. So I really request that you ask your questions directly in the discussion forum. There is a third point I wanted to say, but I forgot. The weekly recordings and the PDFs are now in the Swayam portal. I hope you can find it. It's there in the weekly feedback part of the lesson. So if you want to see where it is, yeah, the problem solving session will be here. So you can just click that and you'll see. You can view it. You can get links, get the folder presentation link and the video link again. So that part of the issue I think I've clarified. Video link. Now one question I had wanted to ask was, I have not yet uploaded week one's mechatronics lessons, and that was essentially because I wanted I wanted your opinion whether I should rewrite some parts of the notes to make it more legible or not. Because some parts of the notes are not quite legible in my opinion, and I would prefer to make it more legible. Like these parts, I wanted to. It's better to be able to see the actual calculations, right? So I thought it might be better if I rewrite some parts of the notes and then I upload it. But that depends on your. It depends on what you guys want. So if you have any specific requirements, I can rewrite the notes and upload it. Otherwise, if I'm personally more comfortable just uploading the.
Yeah, I think what are the lessons like this seat was no only screenshot or compile that PPT. It's enough. No, we can remind that sessions.
Could you repeat?
Yeah, in place of at least entirely rewriting the notes and everything.
Yeah,
The what
it's fine if
this
I just upload whatever is written so far,
that
right?
only the slide PPT is available, that we can remain can be remain be everything also.
Okay, fine. So I'll just upload these as they are. Okay, that's fine. That's better for me. So, and then we looked at some questions about the Grashov's criterion, and I spent a little bit of time making this cute little animation to show how the Grashov's criterion works. Essentially, what Grashov's criterion says is, if the sum of the max and min link lengths is greater than the other two, then pure rotation is not possible. As you see here, right now the sum of the max and min is greater than the sum of the other two links. Like if you see the calculations end up correct, and what happens is for certain values for this range of thetas, no arrangement of the theta is possible. On the other hand, if I increase this so that it's my goodness. So in this case, we get G1 is less than G2, and now it's properly able to. Like the green link is properly able to have a complete 360-degree rotation. That's what Grashov's criteria says. That is, if you're going to have one, only if this G1 greater than G1 less than G2 condition is satisfied, only then will one of the links be able to do a pure 360-degree rotation about the other. So I had unfortunately not changed I had unfortunately not, because if you think about it, it is possible that for this particular set of link lengths, we can also have a parallel set of links which are the opposite way. Instead of here I've made it go upwards, it's also possible to have it go the other way down. And if I had included this, then it would be then I could better show the double crank order. Right now I can only show the crank rocker mechanism, because right now this is the green link is the crank and the black link is a rocker. You can see that with the as the green thing rotates, the black one just rocks around. So it's the parts are clearly visible. If I had included the crank rocker part, then if I had included a crank rocker part, you could have seen that as this goes up, and this would have gone down and continued rocking just the way this was. But I was not able to. I didn't code it in time. That's on me. So that's how you get this would have been the double rocker mechanism. Sorry, the double crank mechanism. Any other combination of G1 and G2, that is, if the Grashov's criterion is not satisfied, you will get a double rocker system. That is, instead of, once it reaches here, we will instead of continuing, we'll make it go all the way back again and go back to this. So essentially we'll have both the green and the black undergo the rocker mechanism. I mean, not rocker mechanism, the rocker motion. So that is about the 4-bar linkage. There are very useful 4-bar linkage mechanisms. Like one very nice mechanism is called the quick return mechanism. So quick return mechanism goes like, it has I will draw it. No, I'll need a new page. So both of these are sliding joints. That is, as the and this is fixed to here. This is a crank. So what happens is, as the crank rotates, this rod is allowed to slide around this joint and this joint. Sorry, this it's allowed to slide along this joint like this and this joint like this. So what happens is, when you're rotating on the further side of the circle, it will slowly go to the other side. So from here, from this angle to this angle, from this angle to this angle, the crank will take so much time to rotate through this region, and in that time, this point, we'll call this where the end effector is. This end effector will slowly move from here all the way back to here. From here to here. And then once the end effector has reached there, it will go to this part of the crank, and at that part, because of how close this is to this point, the end effector will very quickly move from this side to the other end. There are a lot of videos in YouTube to see how this works in reality, and this is very useful. Some people say this is also very important in the industrial revolution, because there are many motions, many mechanical motions we want, that we only have we only put force in one side and not the other. So we always want to spend more time in this way and less time on the other. Yes?
Yeah, there is CAD CAM machines are using these quick return mechanisms.
Yeah, exactly. Cams are also another part which I didn't cover mainly, because there are too many kinds of questions I can ask from it. So And yeah, there are cams also used in quick. There are also cam versions of quick return mechanisms. This is a purely 4-bar linkage method of quick. This is a 4-bar linkage version of quick return. There's also a cam version which I don't remember how it looks like right now. Bolton had a question about cams and it was quite trivial. Like the question is essentially, say you have a roller and a cam which looks like this. What will be the cam will rotate like? The cam rotates like. The cam rotates like this. Yeah. No. The cam rotates like this. Okay. So what will be the output you get from the linear motion you get from this? The linear motion is quite evidently if you think for a while, it becomes kind of clear that the linear motion will be kind of like a step, because over here you'll suddenly jump to the bottom and then the cam will continue rotating towards the left and so on, and eventually once you reach the top, will again fall down. So that will be how the cam will look for this. Another question about the cam was, yeah, if you have a cam which looks like an ellipsoid, sorry, it's just an ellipse. Yeah, if you have a cam which looks like and you have essentially the main reason I skimmed over cams and the 4-bar linkages is because studying this is solidly another course. It's a course called kinematics and dynamics of machinery, and that's not entirely part of mechatronics. So if you were to draw the what's that thing called, the cam output versus time, given a constant velocity here, it will be a slightly sinusoidal, because yeah, we can, it is possible, say you want a very specific kind of speed profile and position profile, it is possible to generate the cam from the velocity profile, but when you're doing things like that, you need to study the angular study the force analysis also, and it'll be slightly more complicated than that. Okay, so that kind of concludes the mechanical actuation part. For hydraulic and pneumatic, we studied a couple of questions from this sort. That is, say the push button is pressed and say push button is not pressed. What happens in the? What are the kinds of things that'll happen? Yes.
Yeah, actually, in that last question session, they asked that compressibility of the this pneumatic system, compressibility of air need to be given, but the option is given compressibility of the fluid. Normally,
Yes.
fluid is we will use as a this system. We will call as a air for that pneumatic system normally.
So I think I said this the last class. Like, technically speaking, air is a fluid.
Yeah, that's correct. But common word we fluid means that the liquid format we can normal.
Yeah,
It was that.
yeah, that
Then
is.
maybe the question was confusing to they put that like that or
Like, I
this one
think they put it like that just to make it confusing.
confusing that.
Yeah.
But the normal case, the fluid will always called as a liquid. Is it correct or?
Like, like personally, I've always learned that fluid can be air also. Like fluid by definition is anything that flows. Like we in mechanics, when you study, we have solid mechanics and fluid mechanics, and fluid mechanics includes both about water and air. So
Okay.
it's perfectly fine to call air fluid, in my opinion.
Okay, it's clear.
Okay.
Thank you.
Yeah.
And this some software now for simulation for this link.
Oh,
Yeah, demo.
that's not a simulation. That's this the program is called Desmos. Essentially, it's just a very nice calculator. But
Okay.
yeah, I had to write everything myself and things like this. It didn't have many. Like here,
So
I've
this
written all
is
the
like
variable.
application software, like
No, it's a free software anyone can use.
okay, Desmos.
Yeah. In addition to Desmos, there's also one thing called GeoGebra. Wait, give me a second. In addition to Desmos, there's also one thing called GeoGebra. I find GeoGebra a lot more scary than Desmos, so I use Desmos. But GeoGebra gives you a lot more power and analyzability. Like in GeoGebra, I can select these two lines and tell you what the angle is between them and things like that, which is very difficult to do in Desmos. I can
Yeah, one
show.
more request of, from our side, I
Yes.
think. This is something you are referred from that some problems like Bolton or Mechatronics.
Could you
So
repeat?
we are like something we in the class we referred some problems from, like you give the examples for the from Bolton or referred the problems. If
Yes.
suppose it was from extrude from that, if you posted here or give that text file or like this, it could be better for we work out after this class.
So the thing is, I am half of the questions here are like, for example, today is one of the first classes I actually used Bolton to prepare the questions because I didn't know how to I didn't want to prepare elaborate questions using torques and gears and drums because all of those are just application of formulae. So I used Bolton for this question also from Bolton. These are also from Bolton, but from a solution manual.
Okay,
The
can you
the
give the reference for that? This one we can get the online that PDF files.
Not really. I'm sorry. Like I believe you have to buy the what's that thing called? You have to buy the solution manual, from what I've understood.
Okay, it is online. We can buy.
I can I refer to this after class? I mentioned this in the first class also, but I don't. I will refer to this after class. I mean
Yeah,
after 7 o'clock.
yeah.
Okay, fine. Yeah, and then after that we also spend a couple of times solving questions like this again. Essentially, we went through the definitions of how directional control works and how these cylinders also work. Oh yes, I was showing you a little bit of GeoGebra. So if I okay, I'll clear this. Uh, so in case of GeoGebra, I can properly write equations. Give me a second. I have to get my. So for example, I can say L, and then I can where more I can add points, and then when I add points, it will tell me where the points are located. I want this to be 0, 0, and this is 0 comma L1 and sorry, that'll be L1 comma 0. And with this I can slowly make the 4-bar linkage. So I have L1, L2 is equal to 0.5, L3 is equal to 0.6, L4 is equal to 0. Unfortunately, like, writing down the equations of the points is actually slightly painful. Oh, it like the equations of the points. Yeah, like the angles are quite weird things. I have to calculate using some weird algebra which I've written here, and I just felt more comfortable writing these equations in Desmos than in GeoGebra. Otherwise, it's actually more powerful to do it in GeoGebra. Like, you have so many more tools. You can easily find measure of angles and things like that. So if you want to use those, I would recommend using GeoGebra. But it's up to you in the end. Then after that, we went and solved. Yeah, we saw this kind of question. That is, given I press this push button, what's going to happen to A and B? And we finally concluded that we slowly went through each of the steps and saw that it goes from A will extend first, and then A will retract, then B will expand, and then B will retract. And then we saw a few questions on stepper motor and the gear shift and torque selection. We derived the angular velocity torque relationship, and I think that's primarily it. I hope that clarifies. I did not talk anything about what's happening in the data presentation part, but I didn't feel like there's any mathematical questions I can ask from that. There's no problems I could generate and solve. There was nothing relevant in Bolton either. Are there any more questions about the yeah?
Yeah, one clarification required. Like when we are giving the answer sheet, okay,
Answer sheet.
yeah, assignment answer.
Yeah.
Sorry.
It's okay.
Sorry. Suppose there is an answer like a numerical number like 2, 3, 4, like this.
Okay.
Some answer is we need to write like 2, 3, 4. Whether we need to write a number or sometime the evaluation sheet they're considering as a string format like 1, 2.
Okay, so essentially, if such a thing happens, then if you get the right number, you can always ask if you don't get marks, you can ask it in the discussion forum saying that you should get marks there. Like
yeah.
It's in the end it depends on what the TAs have. Like, in the end, you're right. It is a string match, so if people are doing other strings, then you will have to include those cases one by one.
Because it was not clear better if the particular question, because if you give the ABC answer, we can easy to select.
Yeah, I was talking to another TA, and they were saying that it's not right to ask for string selection matches because many times it will
better
Yeah,
better they can wherever that like that question is there in bracket they can give use string or use numerical, then we can very clear to the right that
I agree. I agree.
that option we can see sometime what happen after the attending that assignment, if we write that forum also we cannot get the revise the mark.
Like, so I asked the teachers of the other, not teachers, my the higher up, the person I have to respond to, and they told me that I must, you all of you are just are supposed to ask the question in a discussion forum in case there's a discrepancy in the marks.
Yeah,
Like, and
thank you.
unfortunately I can't do anything on my side to change the solutions or things like that. I'm sorry about that. Yeah.
Okay, 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 thank you.
And I would humbly request that you come earlier, like preferably from 5, because I'll be honest, I'm a little more prepared in the first hour than the second hour, especially in today's class, because I unfortunately finished the entire topic in the first hour. Yeah. It would be nicer if you have come early. Mm. So once again, after the class is over, I'll be uploading the recording of this in the YouTube channel. You can get the link in the Swime portal. If there are any other questions, I'm willing to. If there are any questions about the data presentation part, I can answer. Like, one part in the data presentation part is about ASCII, and the ASCII codes are kind of neat in my opinion. Like, for example, in addition to this, small case A, small case B, and all have the second last bit as 1. So while A is 10001, small letter A will be 110001, if I remember correctly. Yeah. And one there are, and essentially that it's not too difficult to understand how the ASCII system works. Like, how am I supposed to do any questions regarding printers? There's no maths here.
Yeah, little bit
uh,
explain that VDU or visual display unit that a
Visual
little
display.
bit confusing that X not this
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 part.
part little bit yeah VDU,
What is the issue with this?
not issue the
uh,
little bit understanding I can't able to understand this the methodology that X factor and Y factor.
so this is mainly about, like, X factor, huh?
No, no, in top itself they given the two
The X
X
flyback, Y flyback.
uh,
Okay, so essentially what's happening is, here we are having, if you think of an old cathode ray tube, we are essentially having a beam of electrons hitting the screen. Now, unfortunately, since a beam of electrons, we can only make points, and therefore, given time, we can only make lines. So, if you want to uh, put if you want to give light to certain regions of this screen, then you have to shoot the beam and at different parts of the screen and just keep doing it. So you will, one way is, where did my, can I draw?
yeah, I got the I was clear now. Something like I was seeing that the television there is a
Yeah,
legal
exactly. So
RHF.
it will just like it's like one cathode ray tube will give a point, and then with time we can make it go to different points on the screen. So instead of doing some different things like going like that, they decided this is the best way to do it. This and this.
Yeah. Got it. In television, there was in old television. If
Yeah.
you see that there is a two buttons was given, horizontal alignment and
Yeah,
vertical.
that's exactly what this is about. Yeah.
Now I got it.
Yeah.
Yeah, clear. Thank you.
Yeah. Oh. So that's about that thing, and I felt this was a very interesting part about non-return to zero and phase encoding and frequency modulation. But yeah, this is essentially the I didn't select the thing. So in the segments, these are, wait, 1 2 3 4 5 6 7, yeah, 7. Yeah, 7 segments. So for for 0, all the segments will be a thing except the except the middle one. So for 1, only these two segments will be highlighted. So it's essentially like A, B, C, D, E, F, G. So therefore you can get like for 2 you need this. So A is highlighted, B is highlighted, G is highlighted, E is highlighted, D is highlighted, and you can see that A, B, C, G, E, and that's basically it. Oh, I could have just done this. Okay. Okay, so that concludes today's class. I am stopping the recording.